Hello, good morning, good afternoon, good evening, whatever time it is where you are. Welcome to this video where we're going to take a look at a problem in mathematics that I've selected from a mathematics admissions test. Okay, so for those of you who are applying to university here in the UK to do mathematics, computer science, and so on and so forth, you may be expected at some point to sit the mathematics admissions test, or the MAT. Okay, so hopefully you're familiar with this. I think I've described it in some detail in some of my other videos, so I'm not going to bother in this video going through all of that again. Suffice it to say that what you're going to be presented with are some mathematics problems that are going to be typically more challenging than the kinds of problems that you would expect to see as part of your normal A-level maths course, either in the classroom, in your textbook, or on your normal maths exams, for example. Okay, so you do have to prepare quite well for the MAT. So we're going to take a look at a problem from one of the past papers in this video, the 2009 MAT, and it's going to be question 3. So this is one of the more structured problems. So if you're familiar with the MAT, the structure of the MAT, then you're aware probably that there's kind of multiple choice problems initially. So the first few problems are multiple choice. Doesn't necessarily make them easier, just a bit shorter. And then you've got some more structured problems where you've got several parts, but they're not multiple choice. Okay, so we're going to be looking at one of the lengthier problems. And I found this problem quite an interesting problem in many ways, although at the same time I was a bit disappointed with it. I didn't feel that the problem told a story. A good problem tells a story. Okay, so there's a flow through it, and there seems to be a point to it. So the problem was interesting in some of the things that I had to think about that I didn't expect to have to think about. But when I looked back over the problem itself as a whole, I just couldn't get a sense of the flow through the problem. Nevertheless, it was a problem on an MAT. And if this is what you're presented with, this is what you've got to do. Flow or no flow. So, just before we start, I'd really be grateful if you could hit the subscribe button for this channel and hit the like button for this video to show your support. I don't make any money from making these videos. As you can probably tell from the production quality of the videos that I upload, or should I say lack of production quality of the videos that I upload, you can probably tell that I don't get paid for making these videos. I make these videos because I enjoy making these videos and because I want to help you to achieve the outcome that you want to achieve with your STEP, with your further maths, or MAT, or whatever it is that you're looking to do. So I'd also be really grateful if you do know anybody that is preparing for exams, maths exams, particularly STEP and MAT, if you would let them know about these videos, share these videos with them because they might find them useful. Just show your support for these. I'd love to continue making these videos, but I can only continue to make these videos while ever there's people that are actually going to be watching them, using them, and so on and so forth. So that would be great. Cheers, guys. So let's have a look at the question itself. So it's question number 3 from the 2009 MAT. I'll leave a link in the description to this video so that you can download the past paper for yourself. The solution that I present is my solution. It's not a mark scheme solution. Unless I explicitly say otherwise, in all of these videos that I make where I go through these problems, the solutions are my solutions. They're not model solutions just taken from mark schemes. The whole point is that I describe the problem-solving process. Okay, that's what I'm really trying to emphasize with these videos, because I think it is something that a lot of people struggle with when it comes to learning about mathematics, because the way that mathematics is often presented to them in textbooks and in the classroom is in a very kind of refined and polished form. Okay, textbooks give worked solutions that are very to the point. And you can understand why it's like that. Teachers in classrooms, because they've got limited time, will get straight to the point. But what it means is that solutions to quite challenging problems are often presented as if the solution just kind of fell out. It almost wrote itself, and that's just not the case at all. If it's a challenging problem, then there's probably been a lot of work actually gone into finding the solution to that problem. And it's really that work that you've got to put in to find the solution that I'm really wanting to emphasize in these videos. Okay, so let's have a look then. So the information that we're given is as follows. For a positive whole number n, the function fnx is defined by fnx is equal to x to the power of 2n minus 1 squared. Okay. And then part I, the first part of the problem, on the axes provided opposite, sketch the graph of y equals f2 of x, labeling where the graph meets the axes. So f2 of x is naturally going to be equal to x cubed minus 1 squared. Okay, so I don't know how much emphasis you personally place on drawing diagrams and things like that, or in the classroom how much you're encouraged to draw diagrams, draw graphs of functions and things like this. It's definitely a good habit to get into. And you also need to develop certain strategies about how to figure out what the graphs of kind of unfamiliar functions look like, or unfamiliar forms of functions and things like this. So here we've got x cubed minus 1 squared. So the way that I would go about sketching this is not to jump straight into x cubed minus 1 squared. I mean, the one way that I could try to draw that is to kind of expand it out, but then I'm going to get an x to the power of 6, and am I going to have to look for turning points? And what you find is that with suitable strategies, often you don't need to differentiate to find turning points. Where the turning points are kind of obvious in many respects. You can kind of logically infer where they're going to be without actually doing the differentiation. So if I start, for example, with the graph of x cubed minus 1, now hopefully you'll know what the graph of x cubed minus 1 looks like. If you don't, well, so what does x cubed minus 1 look like? It looks something like this. Okay, so it's x cubed minus 1. Okay, so translation in the y-axis of 1 unit in the negative direction. So that's 1. This is minus 1 here. Not necessarily drawn to scale. It doesn't have to be drawn to scale. Okay, so what do I see from this? So if I'm going to square the values, I've got to think now what happens when I start to square the values on this, because this is not the graph of f2x. This is the graph of x cubed minus 1. So what I know is that when I square values that are greater than 1, they're going to get bigger. Square values that are less than 1, they're going to get smaller. Okay? Or smaller, the magnitude. Square values that are equal to 1 or minus 1, then I'm going to get 1, right? So here, because x cubed minus 1 goes through the y-axis at minus 1, x cubed minus 1 squared is going to go through the y-axis at 1 here. Because the graph of x cubed minus 1 squared, as x cubed minus 1 goes through the x-axis at 1, x cubed minus 1 squared is also going to go, it's going to touch the x-axis at 1, but also I'm going to get a repeated root. Okay, so here I can see that x cubed minus 1 has a single root at x equals 1, but because of the square now, I know that x minus 1 is going to be a repeated factor of this expression here. So I can include that. So it's going to look something like that. It's just the kind of thing that you would see with a quadratic, for example. Okay, so I can start to figure out what the graph is going to look like. I'm also going to, because I've got a point of inflection here with the graph of x cubed minus 1, I'm going to have a point of inflection with x cubed minus 1 squared. Okay, so and also the values get more and more negative. They're greater than 1 here. Less than minus 1. So when I square them, they're going to be greater than 1. So my graph is going to look something like this, maybe. It doesn't need to be perfect. You just need to get the right kind of shape. Okay, so what I've drawn in red there, it's not necessarily, it will look a bit crappy to be honest with you, but it suffices. It's got all the key information there. You've got a point of inflection here, you've got the turning point here with the repeated root, you've got the intersections with the axes, you've got roughly what the shape is going to look like. It's all there, it's sufficient. Okay, so then I can get rid of the graph of x cubed minus 1 if I want to. And what information do I need to include? I need to labeling where the graph meets the axes. That's easy enough now. So it's going to be at 1 here and 1 here. Okay, and that's it. So down, 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 down. Point of inflection kind of curves around a bit, and then we've got the repeated root there, and off it goes, off to infinity again. So, on the same axes, sketch the graph of y equals fnx, where n is a large positive integer. So I could in theory just, there's a fly here, do a very similar thing to figure out what the graph is going to look like. X to the power of 2n minus 1 minus 1, that's an odd power of x. It's going to have basically the same shape, it's just going to be much steeper. So if x cubed minus 1 was kind of like that, x to the power of 2n minus 1 is going to be much steeper. It's still going to go through, and it's going to be a lot flatter here. And then it's going to grow a lot faster. Okay. So what's the graph going to look like? It's going to have roughly the same shape. It's just that this is going to be a lot steeper up here. It's going to come down. Still going to have the point of inflection. It's going to go down here. It's going to have the repeated root again. This is going to be really flat here until it eventually hits the x-axis at 1. Then it's going to be flat, 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 and then it's just going to explode. Again, it doesn't need to be perfect. Okay, you just need to show that you've taken into consideration the various bits of information, various relevant bits of information. Do not look for perfection. Okay, it's not necessary. Your examiners are not going to be looking for perfection on the MAT. What they're looking for is that you have good ideas, that you have a good understanding of mathematical ideas. You might not necessarily be perfect at following through with those ideas, but as long as you've got ideas you can demonstrate to your examiner and they can see that there's something there that they can work with, that's what they're going to be interested in. Your ability to actually develop ideas, that will improve over time. That's something that can be taught. Okay, but actually having ideas in the first place, there's a certain expectation that you need to be at a certain level with that in the first place. Okay, so that'll do for that. So then it says, part 3, determine the integral from 0 to 1 of fnx dx. Okay, integral from 0 to 1 of fnx dx. Well, okay, it's literally do the integration. So x to the power of 2n minus 1 minus 1 squared dx. Now here I would expand out the brackets, so you get the integral from 0 to 1, x to the power of, what's going to be 4n minus 2 minus twice x to the power of 2n minus 1 plus 1 dx, which is x to the 4n minus 1 over 4n minus 1 minus 2 over 2n x to the power of 2n plus x between 0 and 1. So what does that give? Well, cancel. So we get 1 over 4n minus 1 minus 1 over n plus 1 minus 0. And then tidy this up, what do you get? When you tidy all of this up, you get 2n minus 1 squared over n times 4n minus 1. So just to save a bit of time, I've just copied that from my notes. But it's a fairly straightforward and rudimentary algebraic manipulation to get from here to here. So I'm going to leave out the specific details, and that's that. Okay, we're going to need this at some point, so I'm going to make a note of it. So the integral from 0 to 1 of fnx dx is equal to 2n minus 1 squared over n times 4n minus 1. So that's going to be useful to us in a minute. Okay. By the way, if there's any questions that you have about what I'm doing, please feel free to ask any questions that you have in the comments section. These videos are completely unscripted, by the way. So yes, I've solved these problems previously, but actually most of what I'm saying, in order to try to capture the spontaneity of the problem solving process, I'm still leaving some things actually to do here now on the board as the camera's rolling. And so I'm allowing my thoughts to, I'm trying to express my thoughts as they're coming to me in order to kind of demonstrate the problem solving process in all its messiness. Right? Problem solving process is not a straightforward thing. And it's that messiness that I'm really trying to capture. Okay, so we can get rid of that. I don't need that anymore. We don't need that anymore either. So then we need to show that 3n minus 1... Oh, sorry. Further information. The positive constants a and b... Let me write this up. So a and b, positive constants, such that the integral from 0 to 1 of fnx dx is less than or equal to a over n plus b for all n greater than or equal to 1. It's actually 1 minus a over n plus b. Show that 3n minus 1 times n plus b is greater than or equal to a times 4n minus 1 times n. And explain why a has to be less than or equal to 3/4. Okay. This bit is easy. This bit takes a little bit more work. Okay, let's get the easy bit out of the way then. So it's simply a case of using this inequality here, the expression that we've just figured out, 2n minus 1 squared over n times 4n minus 1, less than or equal to 1 minus a over n plus b, and expand, simplify, try to bring it into this form. And it is simply just a case of just mess around until you eventually get there. Okay. There's no trick to it. There's nothing that you can necessarily do to speed things up or whatever. You just got to do what you've got to do. We know that all of these are positive quantities, so we can just multiply through by whatever we need to. So with 2n minus 1 squared times n plus b less than or equal to n times n plus b times 4n minus 1 minus a n 4n minus 1. Now that's a good sign that we've got this here, and also it's because of the minus sign, when we bring it over here, we're going to get something over here is greater than or equal to this. So it's a good sign, right? So let's do that. Let's add this to each side. an 4n minus 1 is going to be less than or equal to n times n plus. In fact, so I'm going to write it as n times 4n minus 1 minus 2n minus 1 squared, all multiplied by n plus b. So we've got the common factor of n plus b. So that's less than or equal to 4n squared minus n minus 4n squared plus 4n minus 1, which is therefore less than or equal to cancel 1 3n, minus n plus 4n, 3n minus 1 times n plus b. There we go. Okay, easy bit done. Now we've got to explain why a is less than or equal to 3/4, and this took me a while to figure out. It took me a while to figure what I needed to do. I did within a couple of minutes. I just didn't realize, I didn't fully appreciate that I'd done what I needed to do. Okay, I needed some time to think more carefully about what I'd done, and sometimes you can really kick yourself. You can, but this is why it's important really to pay attention to what you're doing and to have some understanding. You might not know straight away, you might not fully appreciate straight away what you've done, but you need to have the capacity and the ability to think and reflect on what you've done and interpret it in a suitable way, so you can eventually come to a realization that you've done what you needed to do. Okay, so I'll show you what I did, and then I'll kind of go through the thought processes that led me to better understand what I'd done. Arguably, I should have seen it sooner, but that's not always the case. We don't live in an ideal world. Sometimes you do things, sometimes you miss what in retrospect seem like really obvious things. And that's just the way that it is. So we've proved this. So what I did was, really because I couldn't think of anything else to do, and I just wanted to get going, I rearranged this so that we've got a is less than or equal to 3, I'll actually write it as this, n plus b times 3n minus 1 over n times 4n minus 1. And which you can then write in the following form, by dividing numerator and denominator by n squared. You get 1 plus b over n times 3 minus 1 over n over n is just 1 over 4 minus 1 over n. Okay, and then what I did is I looked at the limit of this as n approaches infinity. So the limit as n approaches infinity of 1 plus b over n, 3 minus 1 over n over 4 minus 1 over n. And this turns out to be 1 times 3 over 4, which is 3/4. Now, obviously, there seems to be something in that, right? The difficulty that I had was justifying, because the limit of this is 3/4, why would a have to be less than or equal to 3/4? It's actually kind of obvious. What caused me the difficulty here is because if I'd seen this in, say, an undergraduate book on real analysis and sequences and things like that, I think I would have come to my conclusion much sooner. But because I saw this, because this was on an MAT paper, a mathematics admissions test, and at A level you're not really expected to have a thorough understanding of the concept of limit. I wasn't really necessarily, I was trying to look at it more as an A-level student would, an A-level maths student, rather than the kind of stuff that you do when you get onto undergraduate maths. Now, at A-level, you do occasionally come across the concept of limit, but you don't know it in a precise way. It's not presented in a precise way. Limit of a function or limit of a sequence or whatever. It's presented in a very wavy-handy kind of way. Okay, and it won't be until you get onto undergraduate mathematics and you start doing some real analysis that you really start to find out what mathematicians mean when they're talking about limits of sequences. Okay, but it is these considerations actually that you kind of need to have in mind when it comes to justifying why taking this limit does mean that A has to be less than or equal to 3/4. Because what I've shown here is that, yeah, the limit of this sequence is 3/4, and that's irrespective, by the way, of the value of B. My concern was that tells me about what happens right out there as we're going out to infinity. But what about the first few terms? When I say the first few, I'm talking about the first, any finite number. Okay, it could be quite a large number. We could be talking about the first 10 billion terms of the sequence. Because what we're told is that this inequality effectively has to hold for all n greater than or equal to 1. Remember, this inequality is derived from this inequality here. So if this inequality has to hold for all n is greater than or equal to 1, then so does this one. So I was thinking, how does the long-term behavior of the sequence, how can I guarantee that even if A is less than or equal to 3/4, and that guarantees that for large enough values of n, this inequality is going to hold? What about the first few? The first finite few terms. Will this inequality still hold? Because it's got to be for all n greater than or equal to 1. It's not that there's kind of a couple here and there where it doesn't work. It's got to be for all n greater than or equal to 1. So then my attention came onto kind of the first finite terms, and I thought, well, okay, if this is the limit of the sequence, maybe if I show that the sequence is strictly increasing, so each term of the sequence, and I'm talking about this sequence here, is larger than the previous term, then this inequality will hold. Unfortunately, I couldn't do that. Okay, I couldn't show that this was a strictly increasing sequence. Now, I'm pretty sure that there will be some kind of uniform behavior. Either it's going to be increasing or decreasing, at least after a certain point. But I couldn't show that, generally speaking, even including the first few terms, that it's going to be strictly increasing or strictly decreasing. So when I'm talking about the sequence, by the way, I'm talking about this thing here. This is the n. I'm treating this as the nth term of some sequence. Okay, and one of my misunderstandings here, and this was a really serious misunderstanding. I didn't fully appreciate the nature of these constants A and B. Okay, so all we're told is that A and B are positive constants. Now, in my mind, because I'd not really fully thought about this, I'd just kind of gone straight into doing this. I'd not thought too much about the specific nature of these constants. Inadvertently, I was assuming that A and B were kind of arbitrarily chosen positive constants, and this is where my difficulty was coming in. Okay, because if B can be arbitrarily chosen, there's no guarantee that even if A is less than or equal to 3/4, that this inequality is going to hold for all values of n, because I could just choose B to be a really small value or a really large value or whatever as necessary. And that might screw this inequality up, right? But then it dawned on me, and because I did kind of get a glimpse at the next part of the question, but it dawned on me that the value of B is actually dependent on the value of A chosen. Okay, so A and B cannot just be arbitrarily chosen positive constants. There are actually limits on them. Okay, so they might be arbitrarily chosen within a particular range, but it's not all possible values greater than 0. Okay, so we choose a value of A, that will to a certain extent determine what the possible values of B are going to be. Now, evidently, if we choose a value of A that is greater than 3/4, then that will limit the possible values of B so much that there aren't any possible values of B. Whereas if we choose A equals 3/4, that limits the values of B to a certain range. If we choose A is even less than 3/4, then that might limit the possible values of B even further. But the point is, if we choose A, a suitable value of A, that will limit to a certain extent the possible values of B. They're not arbitrarily chosen. Okay, and this is what I kind of missed. So what I was trying to do, and I was still thinking about finite number. I'd shifted my attention from the long-term behavior of this sequence up towards infinity to kind of finite behavior, and now I was kind of looking at the wrong end of the sequence, so to speak. I was trying to find a contradiction. So I was thinking, well, what happens when A is greater than 3/4? So I put A is greater than 3/4 into this inequality effectively, and tried to give a contradiction, which I couldn't really find. Okay, I couldn't really find a contradiction. But then it occurred to me, it really occurred to me that B is not arbitrarily chosen. B is chosen in such a way to ensure that this inequality is going to be satisfied. Okay, so or this inequality is going to be satisfied, whichever. Okay, so the value of A is chosen, determines to a certain extent what value of B, the range of possible values of B, and therefore which value of B you choose has to be within a particular range. So once I'd kind of got past this, and this took a while actually for me to kind of shift my attention back to the behavior at the other end of the sequence up towards infinity. Then things started to fall into place, but still I need to use a fairly precise definition of limit, what it means for something to be a limit. Okay, so if we've got our sequence, so this is the kind of thing that you'll do when you get onto undergraduate maths. You'll do this in a much more precise sense. So we've got, this is supposedly the limit of our sequence, L. Okay, and then we've got our sequence, the terms of our sequence, which, they're going to be around here, whatever. What happens is eventually the terms of the sequence get close enough to the limit. They're in kind of a band around the limit, and they stay within that band. They don't go out of that band anymore. So maybe we get to the 10 millionth term of the sequence, and all of the terms from that point forward are in this sort of band. And we can make this band as small as we want, and eventually, as we move along the sequence, the terms of the sequence will end up inside this band, and all of the terms from that point forward will stay within that thin band. So this band is of width. It's often given the symbol epsilon. Okay, you'll get sick of that symbol when you get onto undergraduate maths. For epsilon greater than 0, if you've done undergraduate maths, you know what I'm talking about, right? Okay, so therefore, let's say that this limit here is 3/4. This is our sequence. This is the limit 3/4. So eventually all of the terms of the sequence are within this band. Okay, so let's assume now that we are going to get a contradiction here. So let's assume that A is greater than 3/4. So if A is greater than 3/4, that means that there must be some non-zero gap between 3/4 and A. Okay, so A might be up here somewhere, the value of A. So all I've got to do to arrive at a contradiction is to show that because there's a non-zero gap between 3/4 and A, I just choose my epsilon band to be such that it's kind of 3/4 plus epsilon is going to be less than a. So if the 3/4 is the limit of my sequence, then my terms will end up inside this epsilon band and therefore must be less than a. But that contradicts this inequality here, right? Because this is saying that the terms of the sequence must always be greater than or equal to a. So if I assume that a is actually greater than 3/4, I end up with a contradiction. Now, this is very difficult to explain if you haven't come across the idea of the limit of a sequence in a precise sense using the epsilon definition and things like this. So I apologize for that. There's nothing I can do about it, but this is the only way that I could really justify. Now, okay, in the exam, in my MAT exam, I probably wouldn't have got as hung up on things as I have here, because I don't think they're necessarily expecting you to know all of this kind of stuff. It's just my inclination is to try to explain things as fully as I can and hopefully actually introduce you to some new ideas. Okay, so even if those ideas do take you beyond the A-level maths and further maths specifications and possibly nudging into undergraduate level stuff, then so be it, right? So I'm not saying that I'm not expecting you to fully understand the concept of limit of a sequence based on what I've said here. What I would suggest that you do, because there'll be plenty of information about this on the internet freely available to you, is do a bit of research about it and come back to it if you don't understand it, and it will start to make a bit more sense, hopefully. Okay, but this is the convincing argument that I've got in mind. How I will communicate this is an entirely different thing. But this was kind of the thought process that I was going through. So the upshot is that we do get a contradiction. If we assume that a is greater than 3/4, we do get a contradiction, but it's quite a subtle way that we get a contradiction. So the only if we can't assume that a is greater than 3/4, we must have that a is less than or equal to 3/4. Okay. But again, b is not chosen arbitrarily. Understand that b has to be so chosen that a does satisfy this inequality for all values of n. So, right. Now we've got that out of the way, let's move on to part 5. Which says that when a is equal to 3/4, what is the smallest possible value of b? So this is exactly what I was getting at, right? B is not arbitrary. It's a positive constant, but it's not arbitrarily chosen. So what do we do here? A equals 3/4. Well, put it into this inequality, right? So 3/4 is less than or equal to n plus b times 3n minus 1 over n times 4n minus 1. And it's basically just solve this inequality, I guess. Actually, no, it's not. It's find the... this is another limit, jobby. Okay, so let's see where we get what we end up with. So 3n times 4n minus 1 over 4 times 3n minus 1 is less than or equal to n plus b. So 3n times 4n minus 1 over 4 times 3n minus 1 minus n is less than or equal to b. And therefore, how am I going to do this? Let's tidy up this expression. So we get 3n times 4n minus 1 minus 4n times 3n minus 1 over 4 times 3n minus 1 is equal to 12n squared minus 3n minus 12n squared plus 4n over 4 times 3n minus 1. Cancel, we get n over 4 times 3n minus 1. So the limit, and I'll do it over here, the limit as n approaches infinity of n over, again, we need b to satisfy this inequality for all n. Okay, for all n. Now we know that a equals 3/4 is one possible value of a that we can choose, such that this inequality is satisfied for all n. So now we're just trying to find a possible corresponding value of b. So this is going to be equal to divide numerator and denominator by n. I get 1 over 4 times 3 minus 1 over n. Oh, that should be a limit as n approaches infinity, which equals 1 over 12. Okay, so in other words, b has to be greater than or equal to 1 over 12, so therefore the smallest value of b is going to be b equals 12. In other words, if we've got a equals 3/4, as long as we choose b to be greater than or equal to a 12th, and it could be, whichever value we choose, then this inequality will always stand. But if we choose the specific value b equals 12, that b equals 1/12, that's the smallest value of b that we can choose. So there's going to be some things that would be really worth you going away and doing a bit of research about when it comes to understanding more fully what I've done in my solution to this problem. Sequences, limits of sequence, definitely something to have a bit of a read around. So strictly speaking, you don't need, when you do the MAT, you don't need to know anything beyond the A-level maths specification. You don't need to be doing further maths, but I would suggest that if you haven't done any kind of reading around the subject and you haven't been exposed to non-specification ideas, you're going to be at a severe disadvantage, because there will be many, many people that will be doing the exam that will know about these things, because they will have found out about them. So you need to make sure that if you're serious about doing well on the MAT and getting into whichever university it is that you want to get to, you're going to have to put the work in, right? You're going to have to go beyond the specification. If it's something that scares you, if it's something that bothers you, and if you're reluctant to do it, then maybe the MAT is not the best thing for you to be doing. And that's not to say that you can't be successful. It's just that you're going to have a hell of a time, to be honest with you. Now, hopefully these videos will help you along the way when it comes to preparing for STEP and MAT and so on. If you would like some extra help with your preparations for the MAT, please feel free to get in touch with me. It is something that I have experience with, providing guidance, support and tuition for the mathematics admissions test. I'd love to hear from you what your requirements are, what your needs are, what your expectations are, and have a discussion with you about how I can help you. So that brings us to the end of the solution to this problem, and it brings us to the end of this video. So thank you very much for watching.